Hi, my name is Mikito Nanashima. Today I'm going to talk about worst-case learning in Relativized Heuristica. This is a joint work with Shuichi Hirahara at NII. So let's get started. This work is deeply related to the programmability of P/poly in polynomial time, where P/poly is a class of polynomial sized circuits. And maybe many researchers can believe that this learning problem is hard because if there is some cryptographic primitive such as one-way functions, then this hardness of learning is implied. And we also know that the hardness of learning implied the statement that P is not equal to NP, but currently the opposite directions are open. And to investigate the hardness of pack learning is one way to investigate the gap between one-way function and P versus NP problem. Because if we can show this opposite direction, then we can also construct one-way function based on NP hardness. Another important and well-studied notion is average case hardness of NP, where we need to solve NP problem with high probability over the choice of the instance, and the instance is selected according to some fixed distribution of instances. And we also know that if there exists some one-way function, then the average case hardness of NP holds. And of course, the average case hardness implies worst case hardness. That is the statement that P is not equal to NP. And we also do not know the opposite directions. So in this sense, these two central notions have a very similar flavor. Then the natural question is the relationship between these two central notions, and especially in this work we consider this direction from hardness of pack learning to average case hardness. This question is rephrased as this. So this implication means that if we have some worst case solver for NP problem, then it is sufficient for a strong pack learning algorithm for P/poly. Then, is this worst case requirement essential, or can we weaken the requirement to the average case requirement? In this work, we studied this question to investigate the nature of pack learning and the structure in the gap between a one-way function and P versus NP problem. Before seeing our results, I explain more background, especially why this direction is non-trivial. First, I will explain the formal definition of pack learning model. So the pack learning model, in the pack learning model, the input is these three notions: the input size, an accuracy parameter, and sample set. This is a set of labeled data, and each X represents the data, and each V represents the label. And each data is selected according to some unknown example distribution, and each label is computed by the function called target function, and this is contained in the concept class for learning, especially in this case P/poly. But without loss of generality, we can assume that such a target function is a circuit of size n squared by very simple padding augment. Then the goal of this learning algorithm is to output the good hypothesis, the function that is epsilon close to the unknown target function in polynomial time. And in this model, learner must learn all unknown target functions on all unknown example distributions. In this sense, pack learning model has two worst case requirements on target functions and example distributions. And this part causes the gap between pack learning model and average case easiness of NP. Formally, the average case easiness of NP is defined like this. So for each NP problem L, and for each samplable distribution D of instances, we can construct good heuristic algorithm for this distributional problem, where the instance is selected according to this distribution D, and the goal is to output the correct answer with high probability over the choice of these instances. And otherwise, this algorithm must output the special symbol bot, which represents failure. And if we can formulate this learning problem as a distributional NP problem, then this direction is trivial. But in learning models, this instance represents, roughly speaking, sample set, and distribution of sample set depends on the unknown target function and unknown example distribution. That's why this distribution is not fixed in advance. That's why it is not clear whether this learning problem can be formulated as a distribution NP problem directly due to the worst case requirement on target functions and example distributions. But recent progress in complexity theory and learning theory implicitly showed that if we relax one of these two worst case requirements, then we can construct efficient learning algorithm for P/poly based on the average case easiness of NP. That's why by these previous results, the natural conjecture is that the average case easiness of NP is indeed sufficient for the back-learning algorithm for P/poly. And in this work, we formally consider this question. Okay, now I present our results. The first result is somewhat positive result. Based on the average case easiness of NP, we can construct back-learning algorithm for P/poly with an additional assumption on example distribution. And our learning algorithm can learn P/poly on all unknown P/poly sampleable example distributions. And the difference to the previous model is this learning algorithm needs to know the upper bound on the computational complexity of the sampling algorithm for example distribution. That's why the time and sample complexity of learning depends on the complexity of sampling examples. In other words, the more resources are needed for learning in more complicated setting. This seems to be quite natural setting, but this part is not captured by the previous formulation of back-learning model. And this result holds even in more challenging learning tasks called agnostic learning. And this theorem is indeed shown by very simple application of a technique in meta-complexity, as I explain later. That's why a natural expectation is by considering more complicated applications of a similar technique, whether can we remove this additional assumption on example distribution. So now we move on to this question. But unfortunately, as a second result, we can show that for such an improvement, we need some breakthrough. Especially, we can show that the relativization barrier for such improvement. In fact, our first result can be relativized, and this result holds even relative to any oracle. But our second result showed the existence of an oracle relative to which NP problem is easy on average, but back-learning is hard. So for further improvement, we need some non-relativizing proof technique. In fact, our oracle separation between average case easiness and back-learning is much stronger. And we can construct an oracle relative to which P8 is easy on average, but even a linear sized circuit is not back-learnable. Even if we allow additional membership query access, weak learning, and almost uniform distribution, and even if we allow this sub-exponential time learning algorithm. So this is a really strong lower bound on learning. And by this result, we claim that non-relativizing techniques are really required for further improvement. In other words, unless we develop some non-relativizing techniques, our additional assumption on example distribution might be essential to relax the worst case requirement for learning to average case requirement. And our techniques in this oracle construction provides another important result in complexity theory. And we can construct an oracle relative to which P8 is easy on average, but UP intersects co-UP cannot be solved in this sub-exponential time. And this result improved the previous work by Impagliazzo. Especially, we can improve this lower bound. And this lower bound is tight because previously Hirahara showed the matching upper bound on this result. That's why by this result, we can show the tight capability of relativizing proof on worst case to average case reduction for pH. Okay, now let's see proof strategies. For the first result, we construct a pack-running algorithm for P/Poly based on the average case easiness of NP. And first, we apply the technique in meta complexity, especially the worst case to average case reduction for gap min KT. Then we can construct an efficient algorithm for this problem, gap min KT. And in this problem, the input is this tuple of the string and time bound. And the goal is to approximate the value called T time-bounded Kolmogorov complexity of X. And this is defined as a minimum program size for generating X in this time bound. Then we use this algorithm for gap min KT to construct weak running algorithm for P/Poly, and we apply boosting technique in learning theory. That's why our technical contribution is to connect this weak running for P/Poly to the problem called gap min KT. And we need additional assumption on example distribution for this direction. So I will explain this part more. But the idea to construct weak running algorithm based on gap min KT is very intuitive. By the well-known hybrid argument, this task is sufficient to construct weak running algorithm, distinguishing these two cases, sample set and random labels. And especially for a given labeled dataset, the first case is the case of sample set. And the second case is the case in which these labels are selected at uniformly random. And if we can distinguish these two cases, then we can also construct a weak running algorithm. So we construct the distinguisher for this problem based on the algorithm for gap min KT. For this, first we define this X and B as a concatenated string. And the idea is to approximate this value for a proper choice of T and additional time-bound delta. And roughly speaking, this value represents the difference of program size for producing X and producing X and B. That's why the additional program size for producing this B. And in the case of sample set, this value is bounded by this value for the choice of sufficiently large delta. Because if we can construct X and if we know additional information of F, then we can also construct B from X and F. That's why the difference for producing B is at the most the description of this target function, and this is bounded by this value. And in the case of random labels, the natural expectation is so in this case, this B is selected at uniformly random from m-bit strings. That's why we need to memory almost all part of B. That's why this delta is very near to M. And if this is true, then by letting this M be much larger than N squared, we can distinguish these two cases by approximating this value. But unfortunately, in general, this does not hold, because additional time-bound delta and additional randomness B may help generate X. And in this case, this value decreases and this delta also decreases. And we applied additional assumption on example distribution to prevent such a case. And in the full paper, we discussed this part in more general case by introducing the notion of expected computational depth of this X. And in this talk, we skip this part. Okay, now let's move on to the second relativization barrier. And for this result, what we did is first, we improved the oracle construction by Impagliazzo, and we show the tight lower bound. Then we slightly change the oracle construction to show the lower bound of running. And in this proof, the core part is the first step. That's why I will explain this part more. And for simplicity, we consider the lower bound on NP problem instead of UP intersects co-UP. First, I briefly explained the idea of oracle construction in the previous work. And this oracle consists of these two oracles. And the first one is a random permutation. And we apply this oracle to make NP hard in worst case. And the second oracle is a restrictive NP oracle. And we apply this oracle to make NP easy in average case. And roughly speaking, this A that is given a non-deterministic oracle machine and input to M and a time bound, this A simulates this non-deterministic oracle machine in the given time bound. And in this simulation, if we allow all the information of F, then this NP oracle becomes too strong, and the NP problem becomes too easy, even in the worst case sense, especially even if we consider the inverting problem of F. But if we do not allow any information of F, then the NP problem becomes too hard, even in the average case sense. And roughly speaking, the idea by Impagliazzo is to give the partial information of F according to the given time bound. And we can regard this application of the partial information of F as a random restriction. And then the average case easiness of NP follows from the switching lemma for D and F, which represent the non-deterministic oracle machine on matching variables. And matching variables is a variable which represent the input-output relations in this random permutation. But the problematic part for the tight lower bound is, in fact, this switching lemma has not good parameter. That's why we need to restrict many values in this random restriction, and it is not sufficient for the tight lower bound of NP. And for the improvement, first we slightly change the oracle construction to apply the standard switching lemma for constant depth circuits on binary variables. But in fact, this standard switching lemma also is not sufficient for the tight lower bound. That's why next we extend this switching lemma to the switching lemma for larger alphabets. Then we slightly change the oracle construction to apply this type of switching lemma, and in fact, this larger alphabet is an essential part to show the tight lower bound in our proof. But to see the reason why this large alphabet is essential, we need more detailed augment of this oracle construction. So in this talk, I skip this part, and if you are interested, please refer to the original proceedings paper. Okay, in conclusion, this work studied the park-running algorithm based on average case easiness of NP, and we construct the park-running algorithm with additional assumption on example distribution based on the average case of NP, and we also show that the additional assumption is essential in relativizing proof techniques. And we also show the tight capability of relativizing proofs on worst case to average case reduction for pH. That's all. Thank you for your attention.